Welcome to this explainer on the 2026 Engineering Guide to Cable Tray Systems. Now, if you've ever looked up at the ceiling of a massive industrial facility, you've definitely seen them. But today, we're going way past the surface. We're going to bust some long-standing myths and show you exactly why engineering these systems demands your absolute full attention.
So, before you freeze your next spec, we really need to bust a massive myth. A cable tray, it's an intricately engineered structural, electrical, and thermal system. It is definitely not just a glorified metal shelf for holding wires. Think about it. When you install a cable tray into an environment, you're essentially building the spine of the facility. It dictates how well your power and data will flow, manages immense heat and weight loads, and keeps the whole place safe. It's a dynamic, living part of your building's infrastructure.
All right, let's look at our structural blueprint for today. We'll start by proving why these systems are more than just a mount. Then we'll dive into choosing your tray type, break down the material chemistry, explore real-world applications, lock in on 4 crucial design constraints, and finally, look at how the Xinma standard puts all of this into global practice.
Kicking things off with Section 1, More Than a Mount, the Engineering Reality. Every single choice you make about your tray is going to heavily impact 5 critical engineering vectors. First up, span capabilities. This is basically the structural physics of how far your tray can reach between supports without, well, collapsing under the physical load. Then you've got fill limits. You can't just treat it like an overstuffed suitcase. If you pack too many cables too closely together, they generate heat. That heat restricts the amount of electrical current they can safely carry, which completely tanks your ampacity ratings. Add in bonding requirements to ensure everything is properly grounded for safety, and of course, maintenance access. Because if you don't engineer for future access, you're just creating an absolute nightmare for the next technician down the line.
Moving right along to Section 2, choosing your tray type. Form meets function.
The 2026 framework specifically outlines 5 distinct tray types: ladder, perforated, solid bottom, wire mesh, and channel. And listen, each of these behaves entirely differently under physical load and environmental stress. A ladder tray gives you maximum airflow and high weight capacity, which is absolutely perfect for heavy power cables. A perforated tray gives you a really nice balance of physical protection and ventilation. Solid bottom? That's all about maximum physical protection. Meanwhile, wire mesh is incredibly lightweight and flexible, and channel trays are your go-to for those specific smaller cable runs. The golden rule here is that you have to match the physical architecture of the tray directly to the demands of the cables inside it. This comparison beautifully illustrates why you simply can't swap a solid bottom tray for a wire mesh one without completely recalculating your load limits and thermal ventilation. Think about it. A solid bottom tray completely shields your cables from dust, debris, or falling objects in an industrial setting. But because it's solid, it traps heat, which directly drops your ampacity rating. On the flip side, wire mesh lets the system breathe perfectly, keeping those cables nice and cool, but leaves them totally exposed to environmental hazards. Every single choice is a careful trade-off between physical protection and thermal dynamics.
All right, Section 3, the material showdown, chemistry and physics.
What's really fascinating here is how we're forced to evaluate steel, aluminum, and FRP, which stands for fiber reinforced polymer, across 4 very strict vectors: density, stiffness, corrosion class, and earthing behavior. Steel is going to give you unmatched stiffness and raw strength, but man, it is dense and heavy. Aluminum, on the other hand, is incredibly lightweight, with a fantastic strength-to-weight ratio, making it way easier to install. And then there's FRP. This non-metallic option completely changes the game for corrosion resistance and earthing behavior, simply because it doesn't conduct electricity the same way metals do. If you happen to choose the wrong material for your chemical environment, your system is literally going to degrade right before your eyes. Which brings us to Section 4, Real-World Applications, where theory meets geography. Depending on whether you're dealing with a highly corrosive process plant or a surgically clean data center, your combination of tray type and material has to be precisely matched to the environment. In a harsh chemical process plant, that FRP material we just talked about, that might actually be your only viable option. Over in heavy power generation facilities, you're likely looking at heavy-duty steel ladder trays to handle massive, heavy power cables over really long spans. Commercial buildings might just rely on lighter perforated or solid trays hidden up in the drop ceilings. And in modern data centers, where you've got tens of thousands of lightweight fiber optic cables needing continuous cooling and routing, wire mesh systems absolutely dominate the landscape. Let's jump into Section 5, 4 crucial design constraints, the specification checkpoint. Now, this is the absolute crux of the matter. There are exactly 4 design constraints that must be mathematically evaluated and confirmed together: span, load, fill, and ampacity. You can't just pick your favorite one and ignore the rest. These form the unbending rules of the 2026 Engineering Guide. The key takeaway here is that you cannot treat these 4 constraints sequentially. It's like a giant puzzle. If you change your span distance, well, you've just altered your structural load capacity. Add more cables to that load, boom, you hit your filaments. Hit your filaments and you trap heat, which instantly alters your ampacity. It is a continuous, interconnected loop of physics. You have to solve all of them simultaneously before you ever lock in your final project specification. That is the only way to ensure structural integrity, thermal safety, electrical performance, and full compliance. Finally, we arrive at Section 6, the Xinma Standard, Global Compliance in Action. Let's take a look at how a major manufacturer actually navigates all this intense engineering complexity in the real world. Shanghai Xinma Busway and Cable Tray Company isn't just stamping out basic mounts. They're engineering comprehensive electrical infrastructures. We're talking everything from their core cable tray systems and busways to highly specialized seismic bracing designed to withstand literal earthquakes, all the way down to intelligent cable management solutions. And they're deploying these advanced systems across all those highly demanding sectors we just talked about: cutting-edge data centers, complex rail transit networks, heavy industrial plants, and massive commercial buildings. And to ensure these structural and electrical systems perform safely across all those extreme environments, Xinma products strictly comply with a really rigorous list of global standards, like IEC 1537 and NEMA VE1. Passing these stringent benchmarks isn't just about clearing bureaucratic red tape, right? It's concrete proof that the system's chemistry and physics are going to perform exactly as engineered, whether it's installed in a freezing European transit hub or a sweltering Asian data center. So, it all comes down to this. Are you treating your cable management as a simple afterthought or as a fully engineered system? The next time you walk onto a job site and look up at the ceiling of a massive facility, don't just see a bunch of metal shelves holding wires. Ask yourself that critical question and look at the infrastructure with a completely new engineering eye. The cables might carry the data, but the tray ensures the entire building actually survives. Thanks so much for joining this explainer, and we will catch you in the next one.